watch yourself up there.
The clock is more important to me.
Okay, so done by 4:30, and it's close to a hard stop because there's another class at 4:40. Okay, thanks for coming today. This is Jeremy Sugerman. He's our last guest speaker in the class. Jeremy comes from Stanford, where he's a graduate student, closer to the end of his graduate student career than the beginning of his graduate school career. Done lots of cool things with graphics and graphics architectures and the fundamentals you hear about today, and also spent a few years working at VMware, so he's got a little industrial experience as well. Thank you very much for coming, and looking forward to your talk.
Okay, great. Thanks, John. Hopefully the mic works.
And hopefully the monitor will start working.
The monitor?
Sorry.
Oh, I blanked it. I cheated. All right, this is a talk about a system we put together at Stanford that I call Gramps. And my advisor's response to that was somewhat allergic, and one of my best friend's responses to that was, this is how I can tell you don't work in industry. But I can call it Gramps, so I do. This particular talk is going to be mostly about some work we did with it in the context of building graphics pipelines and a little bit of generic Gramps parallelism religion. I try to keep mostly on track with the graphics stuff, but some of the rest of it will sneak in. So a bit of background. Most of our formative ideas and opinions from this stuff came from some work we were doing with GPGPU, with funny architectural platforms like Cell, and heavily with ray tracing, and from a summer Kayvon spent up in Seattle working on Pixar's RenderMan. Then we took sort of a reevaluating step back to be a little more grandiose than ray tracing and a little bit more than just what stupid little things do we want to do to the hardware, to frame the question more in terms of we're nearing the point where people around us are making aggressive marketing noises about combining CPUs and GPUs, and the obvious thing to do is just glue them together with faster and faster buses. There's some interesting questions in how you would actually program those things and what's in the intersection of possible and rewarding for making simplifications, making changes to the interface beyond just putting a faster and faster bus there. The people with whom I published the original work are Kayvon, Solomon, Kurt Akeley, and Pat, mostly from Stanford. Kurt's also at Microsoft Research. And this just made it to press in TOG last month after a fairly long history of reinventing itself in different forms. Okay, the setup for this is very much looking at a universe of what we called commodity, heterogeneous, many-core systems. And here's just some stabs at what those words mean to me, mean to us. Commodity means something you could imagine buying for 99 bucks. You could pay more than that for a CPU. You could pay more than that for a GPU, but you can also get one pretty cheap. And consequences are they're kind of black boxes. They're kind of given to us. The question is, what software can we run on them more than what interesting hardware can we invent? Heterogeneous means you've got all of the above for execution units, plus whatever fixed function units people feel like giving you. Some people like fixed function everything. Some people like fixed function compression and encryption are popular to talk about. Fixed function video decode is a popular one. Everybody's got their favorite fixed function unit that they're convinced consumes 10x less power or is 10 times faster or whatever else. So we'll deal with those. And many core means many things to many people. The critical thing it means is that scale out performance is central, which is a way of saying that if you've got 10 times as many cores in a couple years, you need 10 times as much, or at least 9.5 times as much performance. And it's really critical to think about what's going to happen with scale out rather than just making better use of the same number of cores. This distills down to the obvious question anybody would pose after setting it up this way is, how the heck do you use something like this? How do you program it? People have enough trouble with sort of parallel symmetric systems. And I'll identify the status quo of how people program things like this as they write C programs, they write OpenGL or other GPU pipeline programs, or they take a CUDA, OpenCL compute shader, GPGPU style approach to them. Okay, our emphasis coming at this, as I said, as I kind of hinted, is fairly bottom-up. We take the hardware as given, We're targeting people who want to understand the hardware but don't really want to do all of the annoying stuff. I would say we're targeting the C and C++ programmers of the world rather than the JavaScript programmers of the world. Is almost everybody who tells you they have a programming model or a runtime system or an API is envisioning either the audience of C programmers or the audience of JavaScript programmers, and they make entirely different assumptions about their audience based on which of those two camps they're in. And really, the other non-trivial thing to say is that what we're trying to do is not just eliminate a lot of boilerplate code, but really channel people into avenues that can run well on the hardware. Is one of the things the graphics pipeline does really well is strongly incent you and encourage you to write a program that it can run well. And that's immensely valuable. If you want to formulate this in question form, you kind of rearrange the words, you put some imperatives in, and you just say, we're going to build an environment that does these things I just told you. Okay, this talk will be, what is Gramps? What is this thing we built? Kind of how does it fulfill these goals I told you it would? A specific case study and some rendering work we've done and some renderers we've built. Some obvious and non-obvious, but either way interesting things we learned. And if I haven't exhausted your patience and your time, I'll talk a little bit about what I've done since this work. All right. The short textual version of what is Gramps are your applications are framed as graphs or pipelines. You have some stages, which are essentially programs, and you've got some queues, which are how the programs talk to each other. The parallelism between different stages is producer-consumer, which is just another way of saying there's queues. And within a stage, you can parallelize the implementation either data parallel shader style or multi-threaded conventional sort of threading style. Gramps itself handles scheduling of all of these potentially runnable things and handles the data flow, sort of the queue manipulation and making decisions about who to run as a result of what's going into what queues and what needs to happen. For visual learners, this is what Gramps looks like if you're slightly drunk. I cannot do anything about the blurriness. At least I have not yet successfully done anything about the blurriness. But pictorially, it's the same thing. You've got graphs or pipelines, which have stages, which have different programs and names. They're connected by queues, and data flows among them. Gramps sort of makes the stuff between the kernels happen, and the programmer provides the topology and what goes on inside the boxes. If you can't make out what it says, the top one is a very simple cartoon diagram of how raster graphics works. There's a rasterizer, a shade phase, and then someone that does blending. The bottom is a cartoon diagram of how a basic ray tracer works, which has a camera that throws some rays into the scene. Those rays are then intersected against geometry. They're shaded. Shading potentially generates more rays that are thrown into the scene. And so the new rays are intersected, and shading also generates hits of objects, and those are blended and shaded and put into the image. Yes?
What do you assume is the machine model that you're running for each of these? Like, what goes in the, sorry, what's the machine that runs one of these boxes?
Okay, John asked a good question, which is, I said the developer hands you the program that runs in the boxes. What do you assume about them? I'm going to cheat and say we'll come back to that. It's a bit of a forward reference. The operating assumption is that at least one of those heterogeneous execution units I told you will be suitable. And, oh, that's interesting. And so if many of those execution units work, we'll use whichever ones we want. If there's only one place to run the program, we'll run it there. When we talk about what specific hardware configurations we've modeled, I'll talk a little bit more. Okay. So if you just want to talk about this as what happens to a GPU pipeline if you frame it Gramps style, then you get this slide. The graphics pipeline itself is now an app. It's software. Rather than having the connectivity of your pipeline burned into the hardware still has all of the fixed function units it used to have. It still has the FIFOs it used to have, the shader cores it used to have. But the way communication and data and processing flows among them is now specified by software, which is, the way I like to phrase this is that when you can, you want to decouple control and data or policy and implementation, and you want to give as much influence over policy or control to the application, and you really want the hardware or the system or the black box to take care of running those things really well. And this is the separation Gramps tries to establish. I claim that while this sounds radical and crazy, it's not too radical and crazy even in a graphics context. If you go back and look at why shading transitioned from fixed function to programmable, initially there were no choices. There was default shading and it just kind of worked. It had one or two knobs. You could set a color, maybe one texture. That was cool. But then the space of knobs for fixed function shading got out of control. You had a whole bunch of textures that could all be turned off or on. You had programmable sort of register combiners where you could attach one of a space of ops for what operations occurred. And there was this big set of what I think of, my mental mind is one of those big machine rooms with switches and knobs and buttons. And when you got to the graphics shading portion, you'd dial in some combination out of this immensely complicated apparatus and you'd push go. And this collapsed under its own weight. It hit the point where graphics programmers were instead told, just give me a little program and I'll run the program. And this has been immensely popular. And the transition really occurred because there was such a diversity of configurations that were all valid, and there were new and interesting, there was a whole lot of pressure and innovation there. And I'm going to claim you're seeing the same thing with the pipeline topology itself in a graphics pipeline. If you go look at the graphics pipeline, it was pretty static for a long time, pretty much through D3D9 or OpenGL of a similar age. And then people threw in two new stages. You've got stream out and you've got geometry shading. DirectX 11 is threatening to have, I should say. Some of this is secret, some of this is public. I've never actually seen the secret documents. I've just heard what people say, so I treat it as all public. But DirectX 11 is going to have multiple new stages for tessellation, and as a result of having tessellation, you end up with a couple more programmable vertex stages that come along for the ride. And we're going through, basically after years of being static, every successive generation of D3D and GL, it's adding and removing and making optional multiple pipeline stages. So this is what happened with shading. You've got a bunch of new choices. You've got this complicated state machine. At some point it collapses under its own weight and you make it programmable. And so I say, even if this sounds radical initially to say, pull your pipeline out of the graphics hardware and let the app say it, hindsight-wise you can frame it as looking like what happened to shading. What does this mean about what those software-specified pipelines are? They're a lot more flexible because you're not stuck with whatever is burned into the hardware. And they're not quite as portable. Your graphics pipeline itself is an app. And one of the really nice things the graphics pipeline gives you is if you write a program that runs well on one GPU from one vendor, it probably runs pretty well on most GPUs by most vendors. If you're in the business of writing your own graphics pipeline and framing that graph for Gramps, it's going to be somewhat more aware of the hardware. And this just goes back to targeting our audience. If I'm targeting people who want to understand and code to their hardware, those developers are not consumers of the graphics pipeline. They're developers of the graphics pipeline. And each individual graphics pipeline will be somewhat specialized to the machine underneath it. And that's fine. One big note is there's no domain-specific knowledge in anything I've told you about Gramps. It doesn't know what a triangle is. It doesn't know what a pixel is. It doesn't know any of that. So scheduling becomes a question because a lot of how graphics pipelines run fast is they know a whole lot about their data types. And that's a conversation that will come back all through this talk. OK, I'll quickly go through this just from a CPU side. If instead of saying how does this look to GPU people, I ask how does this look to CPU people, it sounds a lot like streaming, which is something near and dear to John's heart, at least in a past life, and is popular with many people who do parallelism. And I'll go through these pretty quickly, but I'll summarize to say the basic goal of streaming, as formulated, was to squeeze every single possible flop out of the hardware. And in order to do that, they wanted things to be predictable, statically known, and pre-transformed and optimized the hell out of upfront, either during compilation or during some pre-launch analysis. And in return, and as a consequence of this, in order to make it predictable, they wanted a lot of bounds. They wanted bounded space needs. They wanted bounded data access. They wanted to predict execution time. And that caused them to work well only with fairly regular apps. Hello. There you go. Gramps takes the perspective that there are many interesting irregular apps, but otherwise the streaming people had a lot of valuable insights. And what it attempts to do is say, in the cases where you can't do this exhaustive and powerful upfront transformation and blocking, try and get it back at runtime as much as possible. Try and use these queues to aggregate up whatever is happening in a data-dependent dynamic way and still find large blocks of work that can be scheduled together, still try and capture all the streaming goodness. It just has to happen at runtime. The other big note is heterogeneity was something that the streaming people never quite got to, is they mostly made up custom chips and they mostly had homogeneous architectures. One little note is that for pieces of a Gramps graph that are statically streamable, it's entirely plausible to just block them all and schedule them statically. We didn't do that, but it's a natural extension. Okay, one brief digression on parallelism in general. I stuck this in here because it's important to me, and I like to talk about it, and it's tangentially related. It's not exactly related, but it should be fast and it should be fun. If I say something that really makes you upset, please challenge me on it, by the way. Is the way I give talks is I take extreme positions, because it's interesting often to see how far a position still has validity, and I tend to have opinions. Okay, so a little bit about parallelism. How to parallelize your app. You take your workload and you break it into separable pieces. You can either do this statically by just compiling a bunch of separate programs or threads that are built in, or dynamically if you have some sort of task system where you just fire and forget new operations as they come up. And then you optimize each of these pieces, which I call sort of internal parallelism, and then you optimize how these pieces interact with each other, how they're launched, how they exit, how they pass data to each other, etc. And I call that external parallelism or sort of interparallelism. There are all sorts of examples: a threaded web server, a shader program, a graphics pipeline. The world is full of examples of parallel systems that are all fairly different. A little bit of how I use terminology: I'll use the word kernel to mean any of those boxes I've shown you before. I'll use it to mean both a shader in the GPU shader sense, or even a thread in a task-based system. In my notion, kernel is just the black box of something that does some work, and I worry about how kernels are connected to each other, which I think of as graphs, which I've already shown you. Okay, so what happens inside these kernels when you want parallelism? There's theoretically a continuum from very heavyweight, coarse threading at one end to lots of trivial, tiny data parallel threads at the other end. In practice, there's a couple of sweet spots that really make sense. I'm going to start with the claim that you can get away with only two different types of parallelism to still cover most of the interesting parts of the space: thread or task parallelism, as I'll use the terms, and data parallelism. And the way I break these down for the intuition is people will tell you that parallelism is about divide and conquer, and task parallelism is really the division phase. You're chopping up your work in some interesting way and repacking it and resorting it or binning it out. And then when you've got it down to whatever digestible sized chunk, you just hit it with some dense code. And that's the data parallelism. That's the conquer phase. There's a little bit of a note here, which is that 2 is a weird number for anything kind of theoretical. People will tell you should have 0 of something, 1 of something, or an infinite number of them. And 2 is therefore an unusual number. And I'll say that it's because of type compatibility. I have one type of thread or task and one type of data parallel task, but they really are not type compatible, so it's not that I have 2 types of parallelism, it's that I have just completely independent things, each of which there's one instance. And just a reminder, since we're trying to span some continuum, we're going to need more than one item anyway, as any basis works that way. Okay, now how do kernels connect to each other? The first thing people learn about how do you connect kernels to each other is just basic dependencies or barriers. It says this kernel must run before this kernel must run after that kernel. Just prerequisites, sort of the same way people sign up for classes. You must take this class first, you must take that class second. There are other cases which are sort of more interesting to me, which I call producer-consumer or pipelines or various other things, which are essentially classes that feed off of each other, where it actually works really well to be enrolled in both classes during the same quarter because you're learning related material, and having to learn it once, forget it, and remember it again is much more exhausting than just learning it once and applying it in 2 places. There's some interesting consequences if you limit yourself to just dependencies and barriers. And it has influences on how you structure your programs. You tend to have long-lived data and very ephemeral instances and stateless instances of your programs, whereas when you have pipeline-style parallelism, you tend to have longer-lived threads and more stateful threads, and the data itself comes and goes. If you're processing workload like graphics that generates a huge amount of intermediate data that never actually appears on the frame, So all of your fragments, all of your vertices, all of the sort of stuff that comes out of the rasterizer. You don't actually want to allocate a buffer and store that ever. You just want to generate it and eat it up as soon as you can, so that the only thing you have to store are pixels. And producer-consumer style parallelism is a great way of doing that. Okay, that's it about parallelism in kind of the abstract, but it helps remind you of what matters to me. Talk a little bit about Gramps. These are what I would call principles or goals or nice to have. This is kind of the Gramps religion, I guess I should say, or the things we want to feel good about. These are the Gramps feel-good items. I want to be able to claim broad application scope, which is to say for a whole bunch of different applications, you'd rather write it in Gramps than roll your own to whatever native bare metal API exists. I want it to be multi-platform, so not only there's some many-core heterogeneous platform that it runs well on, but that for a variety of these heterogeneous multi-core platforms you can run it. I want application performance to be competitive with if you'd rolled your own and written one to the bare metal. I don't want you to lose very much performance for using my abstractions. I just want the world to be better. I want it to be tunable. This is an interesting, there's an interesting whole talk in this side note that tunability is an amazing property of a runtime system or programming model. It's not something you think about very often as a designer, but if you do not build a system where users can learn to be experts and really feel like they can control their programs, they tend to walk away. As you show, this shows up in like why people aren't really deep into using shell scripts or awk or a bunch of things, because there's no real way to be an expert. And that means that you're always sort of just messing around. And the last point is optimized implementations. This is a lesson I learned from Kurt that is interesting and important to me now, which is that if you design a good runtime system or a good layer, it not only informs the applications above it, but it helps the hardware below it, or whoever is below it, build their abstractions better and optimize to run your code better and give them some roadmap and some pointers towards what's interesting in the future. Okay, step one of writing a Gramps program. There's the setup phase, where, as I said, the application defines its graph. It builds its picture of all the different stages, the queues that connect them, and defines all of them, and hands it over to the runtime and says, here's the picture of the world. One interesting note about this is that I keep saying graph, not pipeline. And this causes an extreme allergic reaction in many GPU people, because the graphics pipeline is a pipeline among other reasons in order to guarantee termination. Is whenever there's an explosion of data in the graphics pipeline, you can always stall the producers of the data and just wait until the data drains out the bottom of the pipeline. It's a really nice property of a system. It means you don't ever have to worry about amplification out of control. Gramps accepts cycles. A cycle, such as the one I showed you in the ray tracing graph, means that in the worst case, a pathological app really can amplify data beyond any ability of Gramps to cope with it. I claim it's worth it. I claim it's worth it because of the well-behaved use cases, of which the ray tracing example I showed is one of them. When you write a ray tracer, you would much rather have each ray bounce some variable number of times, but be pretty convinced it's going to converge, because you've chosen the cutoff probabilities and thresholds such that rays won't run forever. You'd much rather be able to do that on a per ray basis than have to statically unroll your graph so that my ray tracer has 5 bounce stages, your ray tracer has 6 bounce stages, my ray tracer has a special shadow stage, etc. You'd much rather be able to frame it generally and let the application in its code worry about whether or not to go through those cycles again. Again, I remind you, I'm targeting people who at least believe they know what they're doing, which means giving them enough rope to hang themselves is okay, as long as they can also use that rope to build interesting things. There's some interesting questions about how you handle failure. If the system gets into a case where there is data explosion, what does it do other than throw up its hands and assert fail? I'll talk about that a little bit when I talk about shaders. Okay, the next thing, queues. There's not much to say about queues. They can be ordered queues, which is what queue actually means, or they can be unordered queues, which is a funny term, but I don't have a better term. Really, it just means that two stages can be communicating asynchronously through something that just buffers work, or you can be very careful that work is pulled off in the order it's put on. Queues operate internally under the hood on things called packets. So even if you think you're filling a queue with fragments, you're really filling it with groups of fragments. And the argument for this is really what runs well on systems is large bundles of coherent work. None of these words is well defined. But the notion is that you want to amortize your context switches in some sense. You want to amortize all of the per element things so that you can do setup once and then run for a while. It's the same reason people do loop unrolling. It's the same reason GPUs have so many threads, is in general you want a lot. And so queues under the hood, yes, John? Okay, so queues under the hood expect the programmer to actually tell them this is the packet size associated with this queue, and I'm going to make sure that my program always gives you work in units of n. Yes, John?
So the ordering constraint, is it that you mark outgoing flow or queue as this is ordered, this is not?
All right.
When you say enforce, like
how does ordering work? Ordering is
how is it specified?
Ordering is specified per queue.
Okay.
And for each queue, it really has the simplest, narrowest possible meaning, which is just don't reveal data to the consumer in exactly the same order it came in. If you have multiple producers and multiple consumers, then whatever order those producers happen to have hit is the order that's shown to the consumers. There's no further structure. Yeah, what's up?
So queues operate under the hood, right?
Mm-hmm.
So there's a hardware manager for the queues, or is it the software manager?
What do I mean by under the hood? This is another slippery question. When we talk about hardware configurations, I'll talk a little bit more. The short version is that if you assume you're writing a Gramps runtime for something like a multi-core processor, you should assume everything is software. If you assume you're writing a Gramps runtime for something more GPU-like, you should expect it to be a hybrid combination of hardware and software. And really, that's true anyway. The only question you're asking is there an explicit queue instruction in the instruction set, or is there some other set of building blocks? And I'll give you kind of a don't care answer. Is if you tell me I want to write a Gramps runtime that can handle queues on a CPU, I'll implement queues out of normal CPU instructions.
So you should have an efficient system of variable-sized, variable behavior queues available to you. So that's all you're asking?
Yes. What I'm asking is that the system be capable of implementing queues efficiently. And really, that it be able of implementing queues efficiently given reasonable packets of work. As the slide says, I'll let you say my packet is one item. You can say I'm going to manipulate this queue in items of one triangle, one pixel, one whatever, and the system will tolerate it, but it's not a performant case to choose for your common case. It's a reasonable case to do sometimes. I'll say that what's in the packet, how those n items are actually expressed and packed and all the rest of it, totally up to the application. Gramps doesn't care. It's not going to look inside your packet. It just wants some notion of how many bytes big your packet is. For the most part, if it needs to dispatch shaders on your behalf, it wants to know how many bytes each sub-element is, just so it can start shaders. Yes, John?
So back to the ordering a little bit. What are you've developed multiple applications here. Like what fraction of queues you have are ordered and what fraction are not? And can you give any indication, maybe this is later in the talk, any indication about the performance differences that you've seen on different hardware with ordering and non-ordering?
The question is, where do I have ordered queues? And then how annoying is order? And the short answer is the only order I have is in Direct3D. Not in the packet tracer, and not in my extensions, and not in some of the other apps I've written since then. And the answer to the second question is that order is incredibly aggravating. Graphics hardware is the only parallel hardware you will ever find where the hardware gives you ordering guarantees. Everybody else considers order a software problem, and there's a reason for it. I mean, order really sucks. We chose to do it in Direct3D that way because it made sense in terms of it's a powerful building block to give the user. You could just as readily expect the implementer of the graphics pipeline to attach his own sequence numbers and then put some form of sort phase in that sorts everything by sequence numbers at the end. That offloads a huge amount of manual labor on the developer of the pipeline and thus runs counter to our people should like to use our system metric. Okay, stages themselves, there's not a lot new to say. A stage can be a shader, a stage can be a thread, or a stage can be a fixed function unit. A fixed function unit, for our purposes, is just a thread that happens to be very highly hardware accelerated. To all the rest of Gramps, it just looks like a thread. The requirement on the hardware designer is that the fixed function unit comply with the queuing discipline. It knows, that is, it knows how to read from a queue, and it knows how to append to an outgoing queue, and whatever it does inside is its own prerogative. So I say there are two kinds of stages. I list three. That's okay. There are not a bunch of funny special data parallel stages. I don't have a scan type of stage. I don't have a reduction shader. I don't have any number of other first-class parallel primitives that parallel programming theory will tell you about. I don't have them because I'm trying to build building blocks that run well on hardware, and I'm trying to build building blocks for people who build engines, not end users. And the right thing to do for people who build engines is to give them the fewest number of building blocks that run well and allow them to compose them to do interesting things. If I give them 4 different ways to solve a problem, all of which have slightly different performance models, that's just irritating, right? It just presents them with a problem they have to solve. And this leads to a healthy amount of minimalism in the design, or what I think is a healthy amount of minimalism and other people think is a paranoid amount of minimalism, but a significant amount of minimalism in the design. Okay, shaders. Shaders are the things for which people who work on graphics have the best intuition. They look pretty much like a CUDA or OpenCL or compute shader thread, plus I give them this push, this essentially variable output option, where they can append to a queue on the fly without having to statically announce how much they're doing. Gramps will automatically instance them, and each instance is non-preemptible. What this means is that if you've got 1,000,000 fragments and you've got, 12 thread slots, Gramps will create 12 threads to handle each fragment. If you've got 1,000,000 fragments and 1,000 thread slots, Gramps will create 1,000 threads. The application programmer does not have to tell you how many threads to create. Gramps figures it out based on what it takes to fill the underlying hardware. Non-preemptible is per instance. It means once I start shading a fragment, that fragment owns its hardware slot until it's done. Doesn't mean any other fragments will get to run, but it means that that guy's going to sit on the hardware until he finishes. And that's just a scheduling simplification. The way shaders are conceptually written, trying to schedule them at a finer granularity is just burns a lot of cycles and creates a lot of churn. The variable output capability I mentioned is like the cycles in the graph capability. It admits pathological cases. It can cause deadlocks if you are trying to operate in a fixed amount of memory. It can create overflow otherwise. I mean, it can consume arbitrary memory, so that will either deadlock or overflow depending on what you want. And just like with graph cycles, I'll tell you it's worth it. I'll tell you that if you don't have variable outputs, you end up running very ugly, uncomfortable compaction phases. And that moreover, if you don't have variable outputs, you can't actually do graphics. So if you look at what makes a graphics pipeline fast, it is the ability to kind of dynamically and variably generate work at some of the non-programmable stages of the pipeline. And so this push notion is actually intrinsic to what makes graphics fast. Yeah?
So you have the heterogeneous platform, and you have building blocks for each stage. My question is, who decides which blocks run on which hardware? Is it programmer, or is it compiler, or runtime library?
Okay. It's a good question, and a question I've gotten before, which is, given all of these stages, how do you figure out where they run? And this answer goes back to the types of stages slide. So the information the programmer gives Gramps is, this thread is a shader, this stage is a shader, this stage is a thread, or this stage is fixed function of type X. So if it's fixed function, you have to tell me what fixed function unit to run it on. And if there's no fixed function unit there that does that, you're out of luck. Which is just, if you tell me you need a rasterizer and I don't have a rasterizer, there's nothing I can do. If you tell me it's a thread, or if you tell me it's a shader, then it's up to the Gramps implementer to decide what to do. Is in one of the versions of our system, the one that is written for just symmetric multi-core processors, we run threads and shaders themselves, both on normal CPUs. In the version that's designed to look like a GPU, even though we have a general purpose processor around, as implementers we made the decision we will only run shaders on the shader cores. So we could try and run some shaders on the general purpose core to sneak in some extras, but we do not. So it is up to Gramps to decide which of its execution units are capable of hosting a thread or hosting a shader, which actually goes back to one of John's questions earlier about what runs where.
The programmer also have to specify which
The programmer has to know which of these 3 categories he's in. Yeah. And then once he tells us a category, we'll figure out where to run it. Okay. Hey, wake up. Wow. PowerPoint fun and games. Better living through PowerPoint. Okay. Threads. After that brief visual digression. Threads are very much what you would expect. They look sort of like POSIX threads. Whatever is inside of what they pull off of the queue is totally up to them. Gramps has no insight into what they do, or sort of no insight into their own type system and formats and the rest. There's, unlike shaders, where I said Gramps will look at how many execution slots there are on the machine and create as many shader threads as it wants to fill the machine. Threads themselves are not instanced. The reason for this is threads are stateful. So if you had a thread that was, for example, doing compression or sorting, and Gramps were under the hood creating more threads, you would have no safe, accurate way to do compression or sorting or anything else because you wouldn't know which set of your data got handed to which thread. There's a bit of a proviso here, which is some of the extended work I've done has ways to instance threads. Threads themselves are preemptible, unlike the shader instances, because, again, they're doing heavier weight, longer, more complicated work. You may want to preempt them and give somebody else the processor. And they operate on these queues directly in place with a simple discipline where they just reserve a chunk of space, read or write from it, and then commit when they're either done producing into it or done consuming from it. Okay. One last interesting thing about the API is we have a concept we call queue sets. And like the Gramps introduction itself, I'm going to do this once for people who like words and once for people who like pictures. So the version for people who like words is that queue sets are all about binning. Is one of the common things that shows up in graphics is you'll chop the screen up into independent regions and you'll put all of your pixels into buckets for each region. And then you'll have, for each region, there's one thread that owns it, and it can pull off of its bucket, and it can update its region without any locks. It doesn't have to worry about some other thread smashing its portion of the screen. It knows it's the only one, but you can have as many threads running as you have regions. And this sort of binning or screen space subdivision or anything else is a very common parallel paradigm for having some synchronization and some parallelism. Gramps expresses this as a queue set, which is a queue that has a number of logical subqueues and an exclusivity principle, so that for each lane of this, for each subqueue, only one thread at a time can be accessing it. But if you've got 100 subqueues that all have data in them, you can have 100 threads, each one on a separate subqueue. And conceptually, you can talk about creating subqueues dynamically at runtime, which starts to get into some of the future work. In the ray trace, or in the rendering work we did, all of the lanes and all the bins were created statically. A bonus, sort of telegraphing into the future, is that you can talk about instancing stateful threads in conjunction with these bins. So you can say that while I can't safely have multiple threads all pulling from one queue, if I give each thread one bin, then that's safe. And so Gramps can automatically create and destroy threads in response to the creation and destruction of bins. Okay, once more in picture form. This is a revision of the picture I showed you before of a rasterization pipeline. It operates kind of how I said in words before. The rasterizer spits out fragments. When it spits them out, it makes a note of which screen tile they're in. They're shaded in just order-free data parallel form, and then they're put into buckets based on which screen tile they're in. The blend unit, the output merger itself, is then also a shader. It's trivially data parallel, except that Gramps itself makes sure that each tile has only one person working on it at a time. So you can have all sorts of blend threads running, and they never have to worry about explicitly locking the frame buffer, as Gramps has assured mutual exclusion. This, by the way, happens all the time in renderers. Is pretty much all fixed function GPUs out there today work this way. This is, I call this tiled or checkerboarded sort last, and is a very familiar architecture to anybody who builds GPUs today. Okay, more specifically about rendering. I'll remind you of the things that would make me feel good. I go to sleep happy if I can satisfy myself on these 5 principles. And I'm going to talk about how we looked at these 5 principles in the context of ray tracing. First one was broad application scope. And I said ray tracing again, I meant rendering. And we have 3 applications. The first application, the first 2 applications are really visible up top. This is a picture of a graph for implementing Direct 3D, mostly Direct 3D 9. There's no geometry shader. It'd be straightforward to put it in. It was just kind of more work. In addition, there's the shaded area on the bottom left, which is an extension we put in that allows you to do variable output and a second shading phase. And we use it to add ray traced shadows. You could also use it for any number of extensions that people have published of what they would do if they had variable output shading. Much of the F-buffer work, for example, you could apply in exactly this way. Like the picture I showed you of Q-sets, it is sort last, which is to say there is this Q-set at the very end before blending rather than earlier up in the pipeline. On the bottom, we have a slight variation on the ray tracing graph I showed before. It's still very straightforward. You generate camera rays, they intersect things. When you're shading, you either give colors to them or you generate further rays for shadows or bounces. And then when you're all done, you go through a very similar blend phase to the output merger in D3D. This blend phase is actually single-threaded the way we wrote it because it's so little work that it's not relevant. We could have put a Q-set there, we just didn't because we didn't need it. Okay, multi-platform. We built Gramps runtime, so to speak, for 2 platforms. The top picture we call CPU-like. You'll note it has a hardware rasterizer. It has a hardware rasterizer just because we didn't feel like writing a software rasterizer, and we already had the hardware rasterizer around for the GPU configuration. The GPU-like configuration looks a little more interesting. The little orange unreadable boxes are what we call microcores. You can think of them as dedicated shader cores. And there's 2 noteworthy things about them. One is that they've got an awful lot of threads. Each one of them has 24 hardware threads. The second is that rather than being scheduled in software, they have this blurry gray box, which is the microcore hardware scheduler. And so if we talk about the implementation of Gramps for the CPU version, it's just a scheduler, the same way you'd schedule any OS or runtime. You write some code, you do some stuff, you have some run lists, you have some priority bits, etc. The simulation in the GPU-like configuration is that that all happens in hardware. And then rather than have a tiny scattering of fixed function vertex setup and this, that, and the other, we slapped one of our general purpose cores onto the GPU and said, we'll just run those other irrelevant parts of the pipeline here because they don't take very much effort. And we wired the whole thing together. We ran both of these graphs I showed you before on Gramps runtimes for these 2 hardware platforms. I said before that Gramps doesn't have the same strong portability that something like a graphics pipeline has. It has reasonable portability, though. We ran those graphs unchanged. The only things we changed about them were certain constants about how big or how many bins there were for the screen. And those were all just a straight function of how many shader threads you could support. They weren't actually otherwise changed. They were a direct function of just how much parallelism in the system. Yeah.
Could you go into slight detail of how your runtimes took advantage of the specific architectures to build the constructs that you
Sure. So
granted for being efficient?
okay. So how do we actually implement these things on these different hardware platforms? On the CPU side, it's just a queue. We didn't waste much emotional angst on could we implement a fast queue for the CPU. On the GPU side, we essentially fiated it. As we said, every GPU in the world is full of very high-speed FIFOs between all of the fixed function stages they have burned into the hardware. So we believe that GPU people are capable of building fast queues. And we'll just make some basic assumptions about their existence and the ability to use them.
But are you asking for variability in their size, number, and the behavior? Don't you think that would add to the performance overhead?
I'm not necessarily asking for variability in them. There's nothing preventing you from chopping the world up into fixed size queue budget, and if you give me a graph with more queues than I can support, you get an error. In practice, I am asking for a little more. And in general, if you look at my requests, expectations of the GPU configuration, they push past where GPUs are today. I'm also expecting my shaders to be allowed this variable output push, which is actually a much bigger deal than asking for a minimal amount of queuing. In all the discussions I've had with different people from the hardware companies, no one has ever seemed particularly nervous about their ability to implement a queue. And so I haven't really stressed too much about it. The points that make them nervous are scheduling, which is conveniently a problem I have not made significantly worse than the problem they have today. I also haven't made it significantly better other than perhaps offering some framework for dealing with it. But I haven't made it significantly worse than today's problem of how do you commingle vertex shaders and fragment shaders and geometry shaders all at the same time. And push, which is a legitimately frustrating demand for people, but I claim is so expressively powerful that you should provide it. And if you don't want it, you can always drop it and forbid any program from using it. I've assumed for the purpose of simulation that it's possible to do at line rate. Okay, so the next feel-good area is performance. And for performance, you have to understand a little bit about how I scheduled these things. Luckily, it doesn't take very much. I can tell you a little bit, and it's sufficient. I looked at the graphs, and I assigned a priority statically based on how close you were in the graph to creating data and how close you were in the graph to pulling data out of the system. And I said, favor the people at the bottom. It's a very simple priority scheme that says if you're near the top of the pipeline or near the top of the graph, try to preempt that person. And if you're near the bottom, or if you're a stage near the bottom, try and schedule that stage. For a graph with a loop, you prioritize the top of the loop over the bottom of the loop, which is sort of an interesting aside that's kind of fun to talk about, and we can talk through later if people have questions. But otherwise, you apply the same principles. With this simple static priority, you then run dynamically saying which queues have work in them and where are my priority conditions violated, and then you just schedule. So the ways we evaluated this, priority number 1, scale out parallelism. I told you this on the second slide, and I haven't changed my mind. Is the fundamental question, the first question, is can you keep the machine busy? Can you fill every execution unit on the machine? The second question is how much queue space did it take you to do that? And this goes back to the question from a moment ago, which is if it takes you gigabytes of fast SRAM in order to queue all this stuff, then it doesn't matter if you can keep the hardware busy. If it takes you very little and it's plausible to cache it, then we can keep talking. The next questions are to start justifying the overheads, justify that you can implement this scheduling policy at a reasonable rate, potentially justify that you can implement the queues, but as I said, I've mostly gotten acceptance that queuing is possible. There are two things that are not at all modeled or implemented today. There's no dynamic change of scheduling priorities. We look at the graph at the beginning, we assign the priorities based on that. Even if one queue gets very full, if it's high up in the graph, we'll ignore it for a while. The other is that there's no serious modeling right now of texture fetch or memory bandwidth. And I claim that texture fetch is essentially a separable problem. Is that if you have a pipeline, however you manage that pipeline and however you manage its queues, you largely have to deal with texture in whichever way you deal with it. Framed another way, if you have a solution for texture that works with a fixed pipeline, that solution should still, to a first degree, apply here. Is all of the special purpose dedicated texture smarts you have apply here, and they apply for my argument that Gramps cares about what goes between stages, and texture really is internal to the shading stage. And so it's basically just part of the shading units that they're capable of doing texture well.
Did you have problems in utilization of different cores that you have?
So utilization is a funny thing to measure. Because utilization, you can make utilization look arbitrarily high by making your optimizer arbitrarily poor. Is one of these awkward tensions. Is the stupider your shader compiler, the better your utilization works. Our fundamental question was, did the scheduler fill all of the thread slots? And our kind of second order question was, are those thread slots doing useful work? And the anecdotal answer is that yes, they were mostly doing useful work. But since I told you we don't have real texture latencies, of course they were. As if I tell you you have infinite speed texture, your shaders are pretty busy too. So
but I'm talking about, let's say you have in a graphics pipeline, what your scene demands of the pipeline determines which of the stages of your pipeline are busier than others.
That's right. You're asking a great question. and I'm just going to smile, and a couple slides from now I will answer your question. And it is a great question, which is that depending on your scene and depending on where you are in the geometry for your scene, the load in the pipeline moves all around. And I told you I had fairly static priorities, so the only thing that would save us here is if just the queues themselves encode what's happening. And the short answer is that they encode some of it. They don't do a perfect job, but they actually help a lot. This data, which is absolutely unreadable, and maybe John will post the slides and maybe you'll care afterwards, is what we got when we measured those two things I told you before. And the short answer is that the queues are small. Is that even for our biggest, most complicated scenes, the 8-core configuration took 600 kilobytes total of queue space. And the GPU configuration took 1.5 meg. And for comparison, the GPU configuration had 100 hardware thread slots, and the CPU one had 32. So it uses more memory just because it's got so many more thread slots. And my claim is kind of if you build a system with 100 hardware thread slots, and that whole thing has to somehow have 1.5 meg of cache, that's not outrageous. And if you have an 8-core system and it has to have 600 kilobytes of cache, that's also not outrageous. So this was not so much this is a slam dunk as our requirements are not outrageous. You can think about queues, or at least the heads of queues, always living on cache, and it's not a big deal. The second note was that parallelism was good. This comes back to John's ordering question, actually, is in something like the ray tracer where there are no ordering constraints and parallelism is free, you fill all the hardware thread slots all the time. In something like Direct 3D where ordering will force you to wait, sometimes thread slots go empty. And they largely go empty because you're waiting for some stupid long-lived fragment somewhere to terminate so that you can start running the next ones.
Can you specifically say what happened in the varied GPU case?
Varied GPU. Varied GPU is actually not too bad. The 20% number is the fat core. So if we look at the picture again, the 20% is this guy, who's just doing vertex setup and everything else. These guys are running at about 81, 82%, which is not significantly worse than anybody else. One of the reasons they're so low is that Fairy is a ray tracing benchmark, which is a polite way of saying it has a ton of little tiny triangles, which is a polite way of saying it won't run on any current GPU very well either. It's got tons of single pixel and sub-pixel sized triangles. So it turns out you don't generate very many fragments that way, and the D3D pipeline is heavily balanced for having a lot of work at the fragment phase. So 80% utilization is not wonderful, but it's not terribly surprising given how bad a scene it is. And also given how bad the scheduler is actually, which is where the slide is going next. So we were here. One other note about order is you'll note the ray tracer has much smaller queue capacity, sort of working set size than D3D. And the reason for that is order. Is the ray tracer consumes in whatever order it wants, whereas D3D suffers what in networking they call head of line blocking. So if a fragment arrives in the queue for consumption, but the fragment ahead of it is not available yet, because for whatever reason it took longer to shade, then all of the fragments behind it will pile up. And I can't dispatch them until I've got the full thing start to finish. So you see these little bubbles form just because people complete out of order and some threads run faster than others. And in the ray tracer, you can consume anything as soon as it becomes available. In D3D, you can't consume a vertex, you can't consume a fragment until all the vertices or fragments before it become available. So that ends up blowing up your working set a little bit. We responded to that by going in and hand-tuning the queue sizes, and that drops utilization. And if you set the queue sizes big enough, then the working set just gets correspondingly bigger and the utilization goes up a little, but the queue sizes go up a lot. Okay. The next thing I told you was important and gave you a little bit of a feel-good speech about was tunability. Tunability manifests in two ways for a system. One is to have the tools to figure out what the hell is going on. The second one is to have some knobs so that when you know what's going on, you have reasonable leverage to apply to change it. In Gramps, the tools you have for figuring out what's going on are basic counters, some statistics, standard deviations, averages, norms about depths of queues, how often out-of-order operations occur, that sort of thing. And a tool we call Gramps Viz, which is every time we make a scheduling decision, we dump a snapshot of the state. And then we play it back as some sort of, essentially a graphical replay of the journal of events that occur. And you can see really interesting things. I'll show you in a moment. In terms of knobs, the three main knobs the application developer has is the graph topology. One example here is that in the course of writing the paper, we completely redid the direct 3D graph. The first version of it we had the Q set between the rasterizer and fragment, and then the rasterizer would directly put things into tiles, and then within a tile we were serialized for fragment work and blend, and that just turned out to have really horrible utilization. This is one of these hindsight obvious things, because as I said, everybody actually builds GPUs the way we ended up with, but for whatever reason we talked ourselves into it the first time. Which was a kind of after the fact, you tell yourself at least you learned a good lesson, is that graph topology is really powerful. There's a big difference between a good graph and a bad graph. The other thing was queue capacity. So there are two ways to size your queues in this system. What people who design GPUs do today is they measure their queue sizes very carefully, build a model for how performance will respond to changing queue sizes, and burn very carefully hand-chosen queue sizes into their hardware. The way I set the queues up for the ray tracer, I set every queue in the system to I don't care, make it infinitely big, and I ran it. Then I looked at my statistics, and all of the queues except for one never got very deep, and that one got ridiculously deep. So I pegged that one's queue size to be fairly small and reran the whole thing. The total usage of memory went down by a factor of 10. Utilization stayed at 100%. So if you're in a universe where you want to deeply understand your application and tune for it, this doesn't matter to you. You've picked your queue sizes, you've set them up front, you want your queues to be full, and you know everything. If you're a lazy programmer like me, you're happy with this universe because you can only set the sizes of the queues you care about, and you kind of trust the scheduler to sort the rest of it out for you. And then the last thing is the packet sizes. As I told you that under the hood, queues operate in chunks. They offer two primary advantages. One is if you're running on a vector architecture, you can make sure you put enough work in a packet so that it matches up well with whatever the SIMD width of the machine is. The other is that within a packet you can share data. So if my packet represents 100 fragments, then I can have the surface shading values and some texture interpolants and other things shared across those 100 fragments all in the same packet. So the packet's a nice element for both getting computational coherence and getting some memory reuse. For the visual learners in the group, this is Gramps Viz. This is the tool I was talking about to figure out what goes on. The blur factor is kind of cool, actually. If you look at this down here, this is what stage of the pipeline is executing. And green roughly means vertex, blue roughly means fragment. If you've ever been employed by a certain graphics design company or a certain graphics card company, these colors are familiar to you, apparently. I didn't know that until someone told me this, but they're not accidentally chosen. Down here, there's the rasterizer, which is mostly idle. If you look at the non-blurry version of the slide, you'll see that there's seas of blue and seas of green, but mixed in with them there is some variance, and you can see that we are dynamically sort of running some blend work, running some shade work. Up here you see the queues, and you can see the effects of order. I'm just going to tell you this. You're going to trust me because you can't see anything on here. But the top line of each queue is how much is available for putting more data in, how much is available to produce into it. The bottom line is how much is available to consume out of it. And if there were no ordering problems, these lines would move in lockstep. Anytime more data appeared for production, there would be less space to consume, etc. With ordering, you'll see sometimes one of these lines goes down and the other doesn't move up. And you see that happen around these sort of humps, actually. Again, this is one of these, you're going to take my word for it, because I'm going to point here and you're not going to see anything. But if you go back afterwards and look at some of these lines, you'll notice that where these gaps appear in the schedule tends to correlate a lot with where you see ordering weirdness manifest in the queues. The other note is this red circle here is really my punishment for my static priorities. Is the way I set up my priorities, when I run D3D, Gramps will try to shade every fragment in the system before it transforms a single vertex. Unfortunately, one of the things we know about raster graphics is that there's lots of fragment work and there's less vertex work. So I've got here 32 threads, and I can produce 32 threads worth of fragment work. Even running at full speed, I cannot produce 32 threads worth of vertex work. Is running at full speed, my vertex setup and everything else can only generate 12 threads worth of vertex work. So my static scheduler screws itself. And it gets into this case where it keeps the whole machine busy, and then you see a pipeline. And this is why you want dynamic scheduling, and why you want, when you get to about here, you want to start trickling the vertex work into the system so that you never have this rigid discontinuity. This was another one of these things we kind of knew intellectually, and until we could draw this picture, we didn't have a strong visceral appreciation of, which goes back to my argument that tunability is really valuable and kind of diagnosability is really valuable. Okay, the last feel-good criteria for Gramps is that the hardware vendor should get something out of it too. They should learn something about it. I'll say that this notion that if you comply with our queuing discipline, then you can plug any fixed function unit you want is a valuable notion of figuring out how to take something like a GPU that is full of fixed function hardware and expose it to a programmer in a way he can deal with. He still can't make it do things it's not capable of doing, but at least he has some way of treating it as building blocks rather than something hardwired. As has been hammered on multiple times with the question, there is room to optimize parallel queues. There's room to learn about, as you build one of these systems, the performance of parallel producer-consumer into queues will heavily dictate the performance of the system. There's also room to talk about hardware thread scheduling, whether you're talking about scheduling the threads literally in hardware or just scheduling a multi-threaded CPU core. There's definite room to take Gramps as a workload and learn about it and kind of go with it. And we are closing in on the end. Now I will mostly just conclude and sort of distill down a couple things that came up, many of which I've mentioned through the talk. Okay, sort of principles of good design that came out, either prejudices we had going in or lessons we learned from screwing up and having to go back and fix it. One is make the application details opaque to the system. There's a whole lot of arbitrary blurring in a today's graphics pipeline between what needs to be in hardware and what just happens to be in hardware. And when you come along and you want to do something else with it, like anything else with it, like even tweak what type of rendering it does a little, it gets really obnoxious really fast. And one of the things that shows up in Gramps a lot is that as much as possible, whenever there was even the shyest excuse for it, we made things opaque to Gramps. We took away domain-specific knowledge. We took away insight into being able to parse the data that was going by, because every time we added it, we ended up encoding assumptions about what types of applications we were going to run and limiting the generality. And as long as we were capable of scheduling without it, we didn't want it.
Can you offer an example? What was something where you made it visible to the system and you said, you know what, that was really a bad idea?
One of the things we talked about was when we were looking at how to assemble vertices back into primitives. We talked about having a DQ mode where you pass some sort of bulk DQ. So the queue coming into you is vertices, and you are setting up for the rasterizer, and you need to know that 3 vertices compose a primitive, or 3 vertices. And we could have had a queue mode where you'd set for the queue on consume mode, only consume in groups of 3. And then we had to figure out what happened if there were odd numbers. And essentially, you see the complexity. You can reason through the complexity. This will ripple through the system. Or I'll tell you what we did instead. What we did instead was we made the consuming end a thread rather than data parallel, and it is allowed to buffer internally whatever it wants.
So it reads 1, reads 2.
Reads 3.
Okay.
If it wants, and this works fine with triangle lists. Now imagine you have a triangle strip, which sucks. In a triangle strip, you see the vertices go by, and every triangle you get 1 new vertex and have to remember the last 2 vertices from before. And again, we could have added a mode to the queue. It was basically triangle strip DQ mode, only we would have been forced to generalize it, so it would have been, remember last n, add 1 mode or something. And we almost talked ourselves into essentially an entirely programmable DQing language before we said this is ridiculous. Instead of doing this, we're going to add threads. And this was the decision that caused us to go from data parallel only to threads, because we'd ended up encoding these weird esoteric things when we would have been much better, or we believe now we were much better off just adding threads and letting the application programmer deal with that.
So one of the issues about going to something like a thread is you're kind of, like a data parallel way, if you could express that in terms of data parallelism, potentially you might have more throughput because threads kind of a serial thing, yeah?
That's a fun thing to say to one of the Larrabee guys. A thread is a serial thing when you have single-threaded core, when you have 1 single-threaded core. when you've got a hyper-threaded, 2-socket quad core, all of a sudden you've got 16 threads just like to not be wasting things in your machine. I view the difference between data parallel and thread parallel as a couple orders of magnitude, but thread parallel should not be thought of as singleton anymore.
Okay. So
and there are other workloads, sort of a digression going back to the ray tracing work we did, is if you could choose how to spend a certain number of dollars or power or transistors of budget, and you could build either a CPU or a GPU, you wanted to build a CPU. This came out when Cell had half as many flops as current GPUs and twice the ray tracing performance. And it was very useful because at the time you couldn't get a chip multiprocessor x86. So the GPU guys were arguing, oh, look, we've beaten it in absolute numbers. And it was true, but they had like a 50x flop advantage and they had a 10x performance advantage, which sort of indicates there's a problem there. And so Cell came along and actually trounced it even though it had a flop disadvantage.
So how, like in your triangle assembly example, how are you using many threads there and keeping ordering kind of constraints? I mean, you're saying it's not a singleton. How do you make that work?
So if you look at, let's go back. This should be possible. If you look at this blurry graph, you can kind of see that the front end is actually broken up into clouds, or what we call clouds, which is there's multiple instances of input assembly and vertex shading. And they actually have sequence numbers, and they all feed into this reorder singleton that will then put them back together. We did this to add parallelism here, to parallelize the front end for exactly these sorts of reasons. And actually, we did it not even just for the triangle assembly, but for the notion of caching transformed vertices. Because if you want to put a vertex in, if you want to talk about a vertex cache, it starts to become even more difficult to figure out how to frame that in terms of queue operations and data parallel stuff. So we ended up with this cloud-like organization. So even though we haven't put the vertex cache in yet, the system is set up so that if I guess the way it says is vertex cache is kind of best practice, and your system should support it. And this is set up enough that it's easy how to drop in a vertex cache while still having parallelism and ordering. So we kind of over-engineered the graph to deal with that.
So are you suggesting that if you go to like your decision was to go from a data parallel stage to a thread parallel stage, but the only way you're able to make the thread parallel stage work is by adding sort of kernel parallelism there and having a reorder stage. Is that a general design pattern that you're using?
I would say it depends. There are other cases where we're using binning, where we're using the queue sets to essentially do group by key, group by screen space, group by something similar. I mean, you can talk about whether I literally say something is a thread or something is a shader. The interesting question is, can the system automatically create more of them, automatically instance them and find the parallelism, or did the user have to do it? And in the case where you have queue set or binning style parallelism, the system can dynamically ramp up and down threads based on how much spare cycles it has. In some case where you're inherently stateful, you're stuck forcing the application designer to manually parallelize his apps. Now, I claim sort of no worse. I haven't made the status quo any worse. Today's stateful thread programmer also has to manually parallelize his app, and hopefully by giving him queues, I've made it a little better. But I agree, I've not made it as much better as I have, for things that can be done in a data parallel way.
Is it fair to say that the system at a very high level, that you as the programmer are going to specify what kind of parallelism is there, as you've done here with some reordering and the flow, and that the system figures out how to exploit that using queues?
I think that's a great statement, that the programmer is expected to understand what type of parallelism his application has, and Gramps is designed to be expressive enough so that he can tell Gramps about all that parallelism, and Gramps can run it on the hardware. And the expectation is, going back to my savvy systems C programmer, sort of gung-ho guy, that he understands his app, he knows what he would do, it's just an awful lot of work to write all of it, and there's no real need to do that work when he can use a system that does it, and that kind of all of the cases where he might be sloppy if he were doing it by hand is done for him. One of the interesting things that came out in some of the MapReduce work that happened at Stanford was they wrote MapReduce versions of apps, and in a couple cases they found the MapReduce version of the app was faster than the native one, because writing the MapReduce version, they just kind of naturally did all of the best practices, whereas in the native one, there were a lot of like, well, it doesn't matter, and it'd be a bunch of code, so we just won't worry about it yet. And all of those things piled up enough to make the hand-rolled version slower than the MapReduce version for some of their apps. So, there's a certain amount of the programmers expected to do it, and there's a little bit of carrot to go with the stick, which is just that I'll make it easy for you to write your program the good way, so hopefully you won't ever do it the slow way. Okay, let's, we've just got a couple minutes left, so we will keep going pretty quickly. This is, as I've already said, I took a strongly minimalist approach to what was in the spec. Kind of push back against everything. Question, is there a simpler way to do it? Are there ways to iron out special cases and generalize them? Q-sets grew out of the same notion of how to deal with kind of binning-style parallelism without making some really gross changes. There's this note of only include features which can run well, with the sort of proviso of sometimes it's something like a graph, it's something like putting a cycle in the graph or allowing push from a queue, where it lets some things run well and some other unfortunate business creeps in. I believe this is a basic tension in systems design, is you can design a system where only good programs can be expressed, but if you do that, then there's at least one program you really wish you could express that doesn't fit. And I don't know, I'm kind of a give people enough rope to hang themselves sort of person, so I would always rather let you express more and then shoot you if you make some bad choices. This is, I don't know, maybe this translates into one's theories on raising children or something. I don't know. Okay, some key traits that showed up in the system was this focus on interstage connectivity and how stages relate to each other, while simultaneously enabling internal stage to do the parallelism, either manually thread it or deliver you these data parallel shaders. But definitely a key focus was between stages. We believe, sort of the stuff I went through in the digression, that producer-consumer is significantly more powerful than only a dependency system. And queues are these amazing tools. I think everybody should know this. I think most people who've written a parallel program already know this. If you didn't know it, you should know it now. Queues are amazing. They're just great, funny little tools. I mean, they're not deep, or hopefully they're shallow, but they are a great way for impedance matching two asynchronous processes and isolating all sorts of heterogeneity and letting them talk to each other. As you can just sort of send messages through this magic, or not magic, but through this very natural mechanism for impedance matching and getting things working. Having threads and shaders, I will claim, is essential. Going back to the discussion John and I had about ending up implementing or walking away from programmable dequeuing, leading to the fact that we needed something stateful, something like a thread, so we could do caching, so we could do rasterization. And at the same time, data parallel is just incredibly powerful. Is when it works, when you can express your program that way, it's just great. But I'll say we stopped there. And this goes back to the minimalism principle, and this is just a manifestation of it. And the final detail slide here is just some little things that showed up, which is that order is very valuable to application programmers, lets you do some powerful things, and it needs to be optional. And largely, the it needs to be optional argument is encoded in the difference in working sets between like the ray tracer and D3D, and just some of the hoops people have to jump through. Q-sets are a great tool because they don't violate the model. If I tell you I have Qs and then I describe this Q-set thing to you, you don't think I made up something weird. But if I tell you I have Qs, oh, and by the way, I have some funny binning parallelism thing tossed into it, you start to get nervous. So I really liked Q-sets because they meant you got this parallelism back while still having mutual exclusion. And mutual exclusion is really valuable in a lot of cases where there's some parallelism but not total independence. And otherwise, I would have needed a separate ad hoc mutual exclusion mechanism. And then the last 2 points are mostly the tunability points, that the user specified queue depth is important. In the ray tracing example, it was optional. I didn't have to specify it, as a good enough scheduler can take things into account. But sometimes the user either knows things that is really hard for the scheduler to learn, or sometimes you just don't want to make the scheduler that good, as you'd rather punt to the user occasionally. And that having the right statistics and pictures really help you understand what's going on. Okay, that's it. Here's a slightly blurry link to the paper. Here's the nice people who gave us money. And thank you to John for inviting me. And let's go through some questions.
So a couple questions. I didn't get a clear sense of, you know, you have a kernel that's this parallel thing, and you got, you know, queues that connect. They move data from one kernel to another. With parallel kernels, there has to be some sort of scatter gather so that you have domain parallelism inside that kernel. And so we didn't see any code examples for any of these kernels, so we don't know what that looks like. My guess is that scatter and gather introduces an Amdahl's constant limit to parallel performance. And did you talk about that in
It was okay. Let me try to repeat your question back to you, both for the purpose of television and to see if I understood what I heard. Which I believe what you're saying is that since the data is coming in from these queues and we're starting up shaders, in order to start a shader, there's some form of gather phase to get its input from the heads of the various queues. We then run the shaders, and then there's some form of scatter phase to fan the output from the shaders back out to the queues. And kind of how limiting is that scatter-gather? Is that what your question was?
Pretty close. The reverse scatter and gather. So you have a kernel, you get a bolus of data coming in. You've got to scatter this bolus out amongst all the parallel bits within a kernel. You do some work, and then you dump stuff out into the outgoing queue, which is a gather phase.
Okay. So let me describe how shaders are launched. Each shader launch on a hardware thread slot is a packet's worth of work. So what we expect to have, if I take a concrete example like fragments, so a packet has maybe 4 times the SIMD width number of fragments in it. And what will happen is, as part of setup, the scheduler will pre-reserve that packet's worth. It will say, we're going to schedule this packet. We're going to say, based on the outputs for this shader, I'm going to reserve this much output space in advance. And conceivably, on the right architecture, at that point, it will then prefetch or double buffer that input so that it's in fast local store. In reality, in this model, you just assume the head of the queue is in the cache, and it happens transparently. Then the shader instance starts up. It operates on its input, which was already in its cache, does some transformations on it, writes its output also into a contiguous chunk of memory, presumed to be in its cache. And then when it's all done, that may get evicted out of the caches back into the queues, but there's not so much of a scatter phase because the output is, you can think of it as blocked, I guess. The output is blocked by the packet size. And so the packets themselves are contiguous, and when we run a group of shaders, they're all operating on elements in the same packet. And that's one of the reasons we use packets to accumulate bundles of work. Does that help?
Yeah, it does. So the answer is that there's block on both ends, basically. So
Yes.
There's no explicit scatter nor gather needed because it's ordered.
That's right. It's blocked into the packets except for the variable output. The variable output is essentially buffered by the system. So we know the packet size, and each fragment can push variable output. We'll accumulate them until either we have to switch to another shader or we've got a full packet's worth of work, and then the coalescing happens there. And so occasionally you will get sparse packets where we'll switch to another shader before we've filled up an entire variable output packet, and then you get slightly worse utilization, but you can still just sort of shove it out and move along. Sure. Anybody else? We're like a minute over, so one closing question or we're done.
So, can you see a situation where a pipeline that some developer designed would, on the field, it would deadlock on some specific application?
Yes.
Is the developer to be concerned about that? Or?
Yes. So the question is, can you get any hard guarantees in this system about deadlock or not? The short answer, if you don't put any cycles in your graph, I'll guarantee termination. If you put a cycle in your graph, I cannot guarantee termination. Every graph with a cycle admits a pathological schedule if the application programmer is determined to do so. There is no magic scheduler, is the short answer. Is the best possible algorithm, if you don't have nested loops, if you have one deep loop, I can tell you the best possible schedule for it, and we can talk about it afterwards. But even with the best possible schedule, a program that amplifies data out of control is beyond, there's nothing Gramps can do to prevent it.
So what are the developers' choices in such a scenario?
Well, I would say that's what is Gramps' choice about failure mode. Today the failure mode is it assert fails. The obvious better failure modes that I mentioned briefly or I alluded to on the shader slide are you can return errors to the shader itself, that shader instance, which I think is a bad idea. You do not want your shader threads to have a ton of error handling code in the middle of them. You can drop the data and return to basically the upstream thread stage, sort of the generator for that shader stage, a note saying something went wrong, here's some state, figure out what to do. Or you can return it all the way back to the host processor and say, this stage overflowed, we had a problem, we gave up on it. And that, I think, is, I'd have to find an app and talk to someone to reason out what good failure semantics were, but those are the most plausible ones. I think if you look at the compute shader OpenCL stuff, they've also started talking about failure handling. But now I think we got to go.